Hi, in this video, I introduce logarithms and use them to solve exponential equations. If you find this video helpful, press subscribe for more contents. Logarithm is basically the opposite of exponentials. Let's take a couple examples in base 2. We could be asking 2 to the third is equal to what? We could also be asking 2 to the 1/2 is equal to what? Or maybe in a different base, let's say base 5. 5 to negative 1 is equal to what? Well, the answer here is 8. 2 to the third means 2 times 2 times 2. The answer is 8. Second question, 2 to the 1/2. Base 2 to the power 1/2. And power 1/2 means the square root. 2 to the 1/2 is square root of 2. You can also write this in decimal as 1.4142, etc. Next, 5 to the negative 1. What is the negative power? Negative power means 1 over. 5 to the negative 1 is 1 over 5. You can also write this as a decimal, 0.2. These are questions that are asked in exponential form. The opposite of exponential would be, I'd be giving you the number 8, and I ask you in base 2, 2 to the power what is equal to 8. So instead of giving you the 3 and asking 2 to the third equals to what, I give you the 8 and I ask 2 to the what is equal to 8. Same with the other two questions. And so the answer would be that question mark is equal to, going to be equal to some function of 8, where that function could be written the opposite of base 2 exponential. And the answer is 3 because you know 2 to a third is equal to 8. So the answer here is 3. Let me put the 8 in red to make it consistent. Well, the shorthand for all of this verbiage is logarithm. It's logarithm of 8. But we also need to specify that we're working in base 2. So I'm going to put the number 2 in the subscript here. And that is equal to 3. I'm going to apply this to the second question. The second example asks a question about the radical 2. So I want to be able to go from radical 2 backward to the answer of 1/2. I want to be able to make it equal to 1/2 like this. And the function in front, again, is the opposite of base 2 exponential. And instead of saying it long like that, I go log base 2 of radical 2. Third example, I want to go backward from 1/5 backward to the number negative 1. Then I use log base 5. If you compare all of these expressions, in the first example, the 3 used to go with the base 2 in the exponential, and the 8 used to be the answer. Once I've written in logarithm form, the 8 goes with the base 2 in logarithm, and 3 is the answer. Second example, the 1/2 used to go with the base 2 in exponential. By the time I rewrite as logarithm, it's the square root of 2 that goes to the base 2 as logarithm. Third example, the negative 1 used to go with base 5 in exponential. Now the 1/5 goes to base 5 in logarithm, and vice versa. 1/5 used to be the answer, and when things got switched, negative 1 is the answer. So the relationship between exponential and logarithm is that the numbers switch places. Whatever number used to go with the base in one form, it becomes the answer in the other form. Therefore, what it means is that logarithm and exponential are the same thing. They express the exact same relationship given a certain base. It's just that the numbers switch places. So in exponential, in an exponential of base a, we'd write things like a to the b is equal to c. If we're going to switch it around, we're going to get logarithm, which most people would just say as log, base a. And these two numbers switch places. The b used to go with the base a in exponential. Now the c goes to the base a in logarithm. The c used to be the answer. Now the b is the answer. And you can imagine going back the other way around. If someone gives you a logarithm like this, you can go back to the exponential form by switching places between b and c. While we're here, let's think back of things we know about exponentials. We like the base of an exponential to be positive. All the exponential graphs and things that you've done have positive base, because when it's negative, it gets complicated. Sometimes negative to a power makes sense. For example, negative 4 squared makes sense. It's equals to positive 16. But sometimes does not make sense. Negative 4 to the 1/2, meaning square root of negative 4, is not a real number. You want a function that makes sense everywhere. You don't want it to make sense in some place and not make sense in others. So for exponential function, we have been defining it as a greater than 0. Or if the base of exponential has to be positive, then the base of logarithm is the same a, so it also has to be positive. Second of all, since a is positive, you take a positive number, you raise it to a power b, the answer will be positive. That means c will be positive as well. A is going to be positive, c is going to be positive. B can be negative, that's no problem. We saw it earlier. 5 to the negative 1 is 0.2. Power b can be whatever, but the a has to be positive and the c has to be positive. That means base of a log is going to be a number a that's always positive. And the c is a number inside the logarithm. It's also going to be a number c that's positive. In other words, if you think in terms of the function y is equal to log base a of some number x, then the domain of logarithm is x positive. Another detail, these parentheses here, they're optional. They're there if you need to group some things. Or sometimes I put in parentheses just because it looks easier to read. If it's unambiguous as to where the logarithm begins and ends, then you don't have to put in parentheses. All right, back to these two equations here. You should take note of them because they are the fundamental definition of a logarithm. And they also give you a way to switch from an exponential to a logarithm and vice versa from a logarithm to an exponential. And we do that by switching places of the b and c. Whatever used to go with the base in one form is the result in the other form. Whatever used to be the result in one form becomes attached to the base in the other form. In the exponential form, b goes with the base and c is the result. In the logarithm form, c goes with the base and b is the result. Vice versa, in logarithm form, c goes with the base in logarithm and b is the result. Switching over to exponential, b goes with the base in exponential and c is the result. Now let's practice switching between exponential and logarithm. We're given these four relationships in exponential. Let's switch them to logarithm. First relationship is 2 to negative 1 equals 1/2, which is true. Negative power means 1 over. Right? We're going to switch places between this number and that number, between the negative 1 and the 1/2. Negative 1 used to go with the base of 2, and now 1/2 will go to the base of 2. in logarithm. So it's logarithm, base 2 in the subscript, and the number 1/2. And in this case, just to make sure that everyone understands that all of 1/2 is inside the logarithm, I use parentheses. And the answer to that is -1. Remember, this also means that it answers the question as 2 to the what is equal to 1/2. 2 to the -1 equals 1/2. Second equality, 10 to a third equals 1,000. Powers of 10 are really nice. When it's a whole number like 3, then you just know that 10 to a third has 3 zeros. Switching places of these two, log base 10 of 1,000 equals 3. Third equality, 5 to the 0 equals 1. And that's true, right? Any non-zero number to the power 0 is equal to 1. Switch places of these two things. And the base is now 5. Log base 5 of 1 is equal to 0. And I can tell that that's true because 5 to the power 0 is 1. The last relation, 8 to the power 1/3 equals 2. Power 1/3 means the cube root, the third degree radical. So this 1/3 and this 2 switch places. The 2 used to be the answer. Now it goes with base 8 in logarithm. Log base 8 of 2 is equal to 1/3. The 1/3 used to be going with the base 8 in exponential. Once I switch to logarithm form, it becomes the answer. So that's how you convert from exponential to logarithm. Now let's do some conversion the other way around from logarithm back to exponential. We're given these 3 equalities involving logarithm. Let's switch them into exponentials. So again, we switch places these two. The square root of 3 used to go with the base of 3 in logarithm. Switching to exponential, it becomes the answer. And the 1/2 used to be the answer in logarithm. Switching to exponential, it goes with the base. And the base is 3, so 3 to the 1/2, like that. Another way you could view this conversion is that the 3 moves over to this side and it pushes the 1/2 upstairs. It moves to the one side and it pushes 1/2 upstairs. Let's now convert the second example. You can think of it as switching these two numbers, or you can also think of it as the 10 moving to this side and pushes the -2 upstairs. And either way, you end up with 10 to -2 is equal to 0.01. And is that true? Yes, it's true. Powers of 10 are really nice. When it's a negative integer, then it just tells you how many decimals there are. 10 to -2 has 2 decimals, 1, 2. So that's true. And if the statement in exponential form is true, then the statement in logarithm form is also true. Let's do the third example. You can think about it as 5 going to the other side and moving the 3 upstairs, or switching places between 125 and 3. 125 used to go with the base is now the results. And I can write it to the left if I want. I don't have to write it to the right. And on the other side, the 3 will go with the base of 5, so 5 to a third. Because we're more familiar with exponentials than with logarithm, it's more convenient to convert things to exponentials so we can tell what the value of a logarithm is. For example, if someone wants to know what log base 5 of 25 is equal to, we don't know what that value is, so we call it x. X equals log base 5 of 25. And then we convert. Then we switch places of these two, or you can think of it as the 5 pushing the x upstairs. Either way, you end up with 5 to the x is equal to 25. Almost home. We make everything into the same base. Well, the left is already base 5. The right, we're going to make it 5 to the power something. 5 to the power 2, because 5 squared is 25. And then we equate the powers or the exponents. They are both base 5, so this x and that 2 must be equal. X is equal to 2. And what was x? X was log base 5 of 25. Log base 5 of 25 is equal to 2. Because we set x equal to the log. A harder example. What is log base 3 of 1 over 27? It's harder, but we'll do it the same way. We set x equal to the log. We convert 3 to the x is equal to 1 over 27. And we need to make them both the same base. 3 to the what is equal to 1 over 27? Okay. I may not know what 1 over 27 is yet, but I do know 27. 27 is 3 cubed. 3 times 3 times 3 equals 27. And how do I get 1 over 27 out of this? I remember. Negative power makes reciprocal. Negative power makes 1 over. So that means this is 3 to negative 3. All right, I got it. 3 to the x is equal to, all of this is 3 to negative 3. I equate the two powers. They must be equal. That tells me that x equals to negative 3. But x is the logarithm. So that means it tells me that log base 3 of 1 over 27 is equal to negative 3. Using the same method, I'm going to compute a couple of special values of logarithm. First, what's the logarithm of 1 in base A? Same approach. I'm going to set x equals to this logarithm. I convert. So either I think of it as switching places between the x and the a and changing the form into exponential, or I think of it as the a going to the other side and push the x upstairs. Let's say I take the first approach, then x becomes attached to the base a, but now in exponential form, and then 1 is the result. Now I need to make them both base a. How do I get a to the power something to be equal to 1? Then I have to remember that I know about this. Power 0 makes 1. This is a to the power 0. And on the right is a to the x. I equate the two powers. I get x equals 0. And x was log base a of 1, so I get log base a of 1 is equal to 0. I boxed this up. This says that logarithm of 1 is always equal to 0, no matter what. And that is directly the result of this. A number to a power 0 is equal to 1. So vice versa, the logarithm of 1 is equal to 0. All right, the next thing that I want to compute is log base a of itself. Log base a of the number a. What is this equal to? I set x equals to the logarithm. I convert. I get a to the x is equal to a. They're already the same base. I just need an exponent. A is a to the first. And therefore, this x and that one must be the same number. X equals 1. And since x is log base a of a, it says log base a of a is equal to 1. Log of some base of itself is always equal to 1. If you graph the logarithm function, you get these. I couldn't type the subscript in decimals, so I used underscore to denote the base. So the top graph in green is log base 2 of x. The middle graph in red is log base 3 of x. And the bottom graph in blue is log base 10 of x. First, you notice that all three graphs pass through this point that has a value of x equals 1 and y equals 0. And that is because logarithm of 1, no matter what the base, is equal to 0. They all pass through the point 1 comma 0. Also, you notice that they grow kind of slowly. And that is because they are the opposite of exponentials. When we say that something grows exponentially, we mean it grows really fast, exponentially. But because logarithm is the opposite of exponential, it grows really slow. At any of these points, if we were going by a straight line, we would have grown faster. It's even slower than linear. And the third point, which is more of a repetition of something I've said before, that is the domain of logarithm is positive x only. So the graph only exists on the positive side of the x-axis. Since logarithm is the opposite of exponential, it means we can use logarithms to solve exponential equations. Let's take these three examples. First one, 5 to the x is equal to 11. Convert it to logarithm. And I get log base 5 of 11 is equal to x. And actually, I'm done. This logarithm is just a number. Some computer will be able to tell us what it is. So once I've arrived at x equals log base 5 of 11, I'm done. This is the solution. If I compute out the decimal of this, I will get 1.4899 rounded. And I can check by taking 5 to the power 1.4899, and I will get 11, also rounded. Depending on what you use the answer for, sometimes you may need the decimal numbers. In a math class, it's perfectly fine to leave it as a logarithm base 5 of 11. Example 2. Do the same thing, convert. Then I get log base 8 of 7 is equal to x plus 1. This is a number. I just need to isolate x and I'm done. And I isolate x by subtracting 1 both sides. If I do that, I get x is equal to log base 8 of 7 minus 1. Again, perfectly fine to leave it like that. You don't have to compute the decimal value if you don't want to. But if you do, you can write it as 0.0642, again rounded. And last example, same thing, I'm going to convert. And I get negative x is equal to log base 10 of 30. And then I take negative both sides, I get x equals to negative log base 10 of 30. Which is negative 1.477 rounded. Actually, this second solution here, it may be better that I put parentheses there so everybody knows the logarithm stops at 7. And once you get that logarithm, you subtract 1 from it. But once you get to a solution like one of these three, you're done because there are computers that can calculate these logarithms for you. However, if you think in terms of several hundred years ago when people first invented logarithm, they didn't have computers. All the calculations they do, they have to do by hand. And all the complicated numbers, they have to pre-print a bunch of tables of numbers for people to look things up. For example, they have to have a table square root so that whenever I need square root of 11, I just look it up in the table and I know what it is. You can imagine that they'll say, okay, we're going to have to make a table of logarithm. We're going to have a big table of logarithm base 5 just to solve the first equation. Oh, look, another big table of base 8 for the second equation, and a big table base 10 for a third equation. And all the other numbers could come up. So base 11, 12, 13, 14. That's a lot of tables. If it takes that many tables, they wouldn't think logarithm is so useful. Why bother with logarithm if all it creates is more problems? So someone thought about it and said, you know what? You don't need all these bases. You only need one base, and everything is taken care of. They chose base 10. And part of the reason why is because having just one logarithm of one base, you can still solve all the exponential equations thanks to the exponent property of logarithms. It says that if you have a logarithm of an exponent on the inside, then you can take the power of it and bring it out to the front. So log base a of b to the power c is equal to c times log base a of b. Let's practice. Let's say that I'm given all of these logarithms. They all have exponents on the inside. Then I can take their power and then I move them to the front. This 4 can be moved to the front, and I end up with 4 times log base 3 of x. The next logarithm, same thing. I can take that exponent and move to the front. That exponent is all of the negative x, so I move all of the negative x to the front. And it's negative x times log base 5 of 3. The third logarithm, all of these exponents can be moved to the front, and I get 3x plus 1 in front and log base 10 of 100. What I need to be careful about is the 3x plus 1 is a whole block, and I'm moving all that block to the front. So once it's moved out to the front, it's still one big block. Therefore, I need a grouping symbol. I need parentheses to make sure that they stay one big block. You can see now how this property helps solve exponential equations. This is something that has x in the exponent, but this one does not have x in the exponent. The x is just sitting on the line like this. It's got multiplied by 3 over here, got added to 1, and it got multiplied by some number there. The log base 10 of 100 looks complicated, but it's just a number. We've just converted an expression that is exponential to an expression that's just linear. Now let's see how this works with log base 10. Log base 10 is called the common log. And we write it as just log without any subscript. So when I write log of x, then what I mean is log base 10 of x. The 10 is unspoken, but understood. On a calculator, the log base 10 key is log. So if I take the exponent property of logarithm and I use it for base 10, and it says that log of b to the power c is equal to c times log of b. The c got moved to the front and multiplied. Now you see how helpful this is. If I have something like 5 to the power x, x is in the exponents. So if I can have the logarithm of it, then I can bring x to the front and it's no longer in the exponent. Matter of fact, let's do that. Let's use the common logarithm and the exponent property to solve this equation that we saw earlier. 5 to the x is equal to 11. If only we have log of 5 to the x, then we can take the x here, we move it to the front, and we end up with x times log 5. And log 5 is just a number. But we don't have log of 5 to the x, we only have 5 to the x. In order to introduce logarithm into the equation, we'll take logarithm both sides. On the left, we have log of 5 to the x. And on the right, we have log of 11. When you have two things that are equal and you do equal things to them, the result will still be equal. On the right, log of 11 is just a number. On the left, we have log of 5 to the x. We can move this x to the front. That makes it x log 5 is equal to log 11. Log 5 is a number. Think of it like 6. It isn't 6, but in your mind, you can think of it as it's a number just like a 6. Log 11 is also a number. It's definitely something you can punch into a calculator and find out. So think of it like a 7. If you have an equation that is x times 6 is equal to 7, then you can always divide both sides by 6 and get x out of it. So since log of 5 is just a number, I'm just going to divide both sides by log of 5. So the log 5 cancel, end up with x is equal to log 11 divided by log 5. And since both log 11 and log 5 are just numbers, I'm done. I can box it up. If I really want to, I can punch this into my calculator. And I end up with 1.4899 rounded. Same answer as before. But I definitely can just leave it as log 11 over log 5. Okay, at this stage right here, x log 5 equals log 11. If you're not yet comfortable with treating log 5 and log 11 as just numbers in your head, then what you could do is you punch things into your calculator. You find out that log 11 is 1.04139. And log 5 is 0.69897. Then you rewrite your equation as 0.69897x equals to 1.04139. You divide both sides by the 0.69, etc. And you end up with this fraction that you can compute. And that's okay. But I don't want you to do that. Maybe do it the first 2 or 3 times. But I want you to get used to the idea that an expression, that the logarithm of a number is just another number. You don't need to think of it in terms of the decimal. You can just leave it as log of 11. And I want you to get used to doing things like dividing both sides by log of 5 and canceling the log of 5 against each other. All right, let's do a harder problem. 3 to the power 2x plus 1 equals 8. It starts out the same way. Take log both sides. Log of 3 to the 2x plus 1 is equal to log of 8. The parentheses are optional. Use the exponent property to bring the 2x plus 1 to the front. The parentheses around these 2x plus 1 are not optional. You need them to make sure 2x plus 1 remains one block. All right, once you are at this step, log 3 is a number, log 8 is a number, and x is on the inside of these parentheses here. I want to isolate x. I want to free it of the log 3 on the outside. Seems like a good idea to divide both sides by log 3. These cancel, and I have 2x plus 1 is equal to log 8 divided by log 3. Well, log 8 divided by log 3 is just one big number. Again, if you're not comfortable leaving it like that, you could take out your calculator and divide the two decimals. But I'm going to leave it like this, and I'm going to isolate x by subtracting 1 both sides. Then I have 2x is equal to log 8 divided by log 3 minus 1. And divide both sides by 2. Well, dividing by 2 is the same as multiplying by 1/2, so I'm going to write it as 1/2 like that. X is equal to 1/2 of log 8 over log 3 minus 1. All right, I want to show you something interesting. If you're in a study group with a friend, you may have a friend that also does perfectly good math and end up with an answer that looks differently from yours. That's perfectly normal. This happens all the time. You could be solving an equation and you end up with 3/2 and your friend ends up with 1.5. They look different, but they are the same number. Same thing here. Your friend could be solving it differently, end up with an answer that looks different, but it's the same number. Let's start here. 2x plus 1 times log 3 is equal to log 8. We need to isolate x, and my approach was to cancel out the log 3 on the outside by dividing it. But someone else may decide, you know what, if I'm going to liberate x from inside the parentheses, I'm going to distribute the log 3 to break up the parentheses. So if I distribute, I have 2x log 3 plus log 3 is equal to log 8. Log 3 is a number, log 8 is a number. There's a plus log 3 here, so I'm going to subtract it both sides. End up with 2x log 3 is equal to log 8 minus log 3. I have my x multiplied by one number on the left and another number on the right. I'm going to divide them off. I divide by 2 log 3 both sides. The 2's cancel, the log 3 cancel, and arrive at x is equal to log 8 minus log 3, the whole thing divided by 2 log 3. Both of these answers are perfectly legit. And in fact, they are exactly the same answer. If you start with this answer here on the right and you do some common denominator, you will end up with the answer on the left. They are exactly the same thing. But it's a reminder that the more advanced you go in math, the more likely it is that you and your friend, or you and the answer in the back of the book, are both correct, but they look different. All right, the last thing I want to talk about is that when people discovered that they could have just one base and use that one base, why did they pick 10? Why not some other number? Because powers of 10 are nice. You may notice that I've said that a few times in this video already. When 10 is raised to a whole number, whatever that number is, it tells us how many zeros there are. 10 to the first has 1 0, 10 squared has 2 0, 10 cubed has 3 0, and 10 to the fourth has 4 zeros. When you go negative, whatever that negative power of 10 is, it tells us how many decimal digits there are. So 10 to negative 3 has 3 decimal digits. You convert all of these into logarithm, base 10, then what you get is this. You get all of these logarithm. And so if you're dealing with some quantity, So for example, if I'm working with some quantity t and I take the logarithm of it, and I find out that the value of the logarithm is, let's say, 3.14, then since I know the 3.14 is around here somewhere, that tells me that t is around here somewhere in the thousands. Just by seeing that the logarithm of t starts with 3, I know that t itself, the quantity that I'm working with, is somewhere in the range of having 3 zeros, meaning it's some thousand. It's not as high as 10,000, but it's in the thousands. What people say for this is the order of magnitude. The logarithm base 10 gives me the order of magnitude of the number. I look at the logarithm, I know right away how big my quantity is. That's why in real life, people like log base 10. Now, engineers, physicists, and mathematicians work with logarithm of a special base called E, letter E. Letter E is a decimal number equal to 2.71828, etc. And the reason why scientists and engineers and mathematicians use this strange base is because the logarithm to base E happens to behave very nicely in calculus. Here's a summary of everything we've talked about today. I hope this helps. Subscribe for more contents. Bye.